what is the total cross section equal to? You integrate over all angles everywhere, then the total cross section is simply going to be total cross section sigma equal to integral d sigma over d omega, which is equal to, and this is over the polar angle as well as the azimuthal angle. There is no dependence on the polar angle here, that gives you a 2 pi. Yeah. So this is equal to 2 pi integral minus 1 to 1 d cos theta mod f of k squared. This is a sin theta d theta from 0 to pi, which I prefer to write in this form. Okay. What is the physical dimension of this quantity? What are the physical dimensions of that quantity? Well, go back here. We wrote in our normalization, we wrote psi incident as e to the I k dot r, which is a dimensionless quantity, plus psi scattered, which has to be dimensionless. This is dimensionless. This guy here has dimensions of length, so this has dimensions of length. The scattering amplitude has dimensions of length, and the cross section is mod squared of that. So this has dimensions of an area, and that is the reason for calling it as cross section. We can compute what this quantity is for a classical beam of particles, for instance, literally calculate it. What happens if I have, for instance, a hard sphere of some radius r and I have a beam of particles coming in? What is the geometrical cross section of this problem? Pardon me? Yeah, all you have to do is take a cross section, it is just pi r squared, right. But if you do this with waves, classical waves, then what is the cross section going to be? You have got to include diffraction effects. In fact, under diffraction there is going to be a maximum at this point here by constructive interference at this point. Classically it is in the shadow, but of course you have shadow scattering once you have waves, and then the number is greater than pi r squared. We will see, we will try to find an example and do this for a hard sphere, put in an actual hard sphere and scatter waves of it and see what this is. Then will come this problem of, does this radius capital R gives you a length scale, k gives you a length scale, and now we have the question of, is kr bigger than 1, smaller than 1, etc., and then you have different answers. We will see what it is. We will see that it can become as large as 4 pi r squared out here. So once you include diffraction effects, but anyway, this is now the formula for the total cross section. What is the next job? We need to find this scattering amplitude. We need to find out what is it. I mean, how am I going to start with the Schrodinger equation and find this scattering amplitude explicitly? In other words, all this is true regardless of what the potential is, but now we got to really find out how does the scattering amplitude depend on the potential. For that, yeah.
So d sigma by d omega is in some sense the fraction that is scattered in a particular solid diameter.
That's right, yeah.
So the integral of it will actually be the total amount scattered?
The total amount scattered, yeah. Total scattering cross section, namely effectively what is this potential acting as? Suppose you did it completely classically, how big an object is this potential, so to speak, for waves which have a certain characteristic wave number k? That is the question being asked. Okay, so let us try. Now we got to go back. Now we have no choice, but we have to go back to the Schrodinger equation and write the equation down and try to solve it. And the time independent Schrodinger equation is of course minus h cross squared over 2m del squared psi of r plus b of r psi of r equal to, since we are looking at stationary states and there is an incident energy which is conserved, that is the eigenvalue of the energy of the Hamiltonian, so E psi of r. This guy here is given to you. Okay. And we are looking at those cases where E is positive, that is the continuous spectrum of scattering states. Just to go back, remember what happens in the hydrogen atom problem. If you plotted r versus the potential V of r, this was a minus 1 over r potential, an attractive potential, and it looked like this, and this is an energy scale here. If you plotted what are the values of the energy eigenvalues, then you have one value here, the ground state, which is minus 1 over n squared in Rydberg units, and then the next state where n is 1, so you have minus 1, the next one is minus 1/4, and then minus 1 over 9. There is a 1 over n squared spectrum with a minus sign for all the bound states. This is the ground state, the first excited state, etc. And then as you tend towards 0, the number of states, there is an accumulation of these bound states, and you can also have any positive value. This whole thing is a continuous spectrum here. Those that corresponds to the scattering of an electron of a given energy of the proton without getting captured. So that is the spectrum we are looking at now. We are looking at the continuous spectrum. Any given positive value of E, I want to know what the scattering is, what the wave function looks like. Okay. So this is the problem we want to solve, and the way we are going to do this is to use something called perturbation theory. So the assumption is that I would like to keep track of the powers of the potential, the strength of the potential relative to the incident kinetic energy. To facilitate that, let me put a coupling constant lambda here, a constant here that measures, if you like, the strength of the potential. Because I am very often going to be loose in writing V of r, I am going to write it as 1 over r, which is not the right physical dimensions. So this lambda constant will take care of all those dimensional constants. Besides, if lambda is 0, then it is a free particle, and as I turn the strength of lambda up, it becomes a stronger and stronger potential. So I want to keep track of this, and for that purpose let me put this constant here just for bookkeeping. Okay. Now this is the problem we want to solve, and the way to do this is to first write this as del squared psi, let us take the minus sign there and bring it back here, plus 2me over h cross squared psi equal to 2m by h cross squared v lambda v. Let us write the lambda outside, 2m by h cross squared v of r psi of r. Let us write it in this form. This is a function of r plus this. I have moved the potential to the right hand side for the moment. Okay. But this you will recognize is precisely the Helmholtz operator. Okay. Equal to, I need a name for this fellow, so let me call this lambda u of r psi of r, where I have just absorbed this quantity 2m by h cross squared v of r. I just redefine my potential, absorbing this constant in there. This looks like the Helmholtz equation, the inhomogeneous Helmholtz equation, with one difference. This is not a given function. This involves the unknown function itself, right, because this is after all an eigenvalue equation, and I have just rewritten that eigenvalue equation. But suppose for a minute you pretend that you know the right hand side. What happens then? Then the solution of this equation is exactly that for an inhomogeneous equation with some particular integral and a complementary function. So I would expect the solution of this equation to look like this: psi of r is equal to an integral d3 r prime, the Green function for this operator g of r prime, multiplied by lambda. So there is a lambda that is going to sit here, and then u of r prime psi of r prime psi of r equal to this. That is the particular integral where this g of r prime is precisely the Green function for this operator plus a complementary function. So this is the particular integral, and then there is a complementary function. And what should that be? Well, I already know what the boundary condition is. I want it to look like psi incident plus the scattered portion. The scattered portion comes entirely because there is a potential, that is the second term. So I want this guy here to be e to the I k dot r. As I have explained earlier, the purpose of adding the complementary function, a certain amount of the complementary function to the particular integral, is to ensure that the function satisfies the specified boundary condition. My boundary condition is that asymptotically this guy had better go like e to the I k dot r plus f of k comma theta e to the I k r over r. It should go in this fashion. So the trick is to start with this, find the Green function, put it in there, and then let it go to this limit when little kr is much bigger than 1, and extract by comparing with that form what this f of k comma theta is. That is going to be the strategy. Now this is not a solution for psi of r, you have to appreciate that very clearly, because the same psi of r appears on the right hand side. What it is, however, is an integral equation for psi of r. I have started with a differential equation, and once I find that Green function, then I have an integral equation for psi of r, which is as hard to solve as the differential equation, but I am not going to really try to solve it immediately. I am merely going to try to find the asymptotic form out there. Okay. But I would expect that whatever I do, I cannot get away for finding this f of theta exactly, I cannot get away without finding the solution to the Schrodinger equation. I need to find this psi somehow. But what equation does this Green function satisfy? Clearly it satisfies del squared plus k squared g of r comma r prime equal to a 3-dimensional delta function on this. Okay. Now that is easy to see, because all I have to do is to apply this del squared plus k squared on either side. I apply that here, and that goes to 0. This is the homogeneous equation after all, and that acting on this, if it is a delta function, will give me precisely this. Okay. So it is immediately clear that I need to solve this Green function equation with some specified boundary conditions. The boundary condition I want is the natural one, namely g tends to 0 as r tends to infinity, because this guy after all goes to 0 on this side. Now this del squared operator is translation invariant. I can shift from r to r minus r prime, and the del squared with respect to r does not change. The delta function is translation invariant, it is a function of r minus r prime already. The boundary condition is translation invariant, it is a function of r minus r goes to infinity, same as r minus any finite r prime going to infinity. So both the boundary condition as well as the right hand side are translation invariant, and the differential operator is translation invariant. So now I can assert that this Green function is also a function of r minus r prime. So let us do that as we normally do. So we write this del squared plus k squared g of r equal to delta 3 of r, where r is r. How would you solve a thing like this? Exactly as we did in the case of this guy here, del squared alone. I do Fourier transforms that converts the del squared into a multiplication by the square of the wave number, whatever it is, right. I have already used k for this symbol, so let me write g of r equal to 1 over 2 pi whole cubed integral d3, let me use q instead of k for the Fourier transform with respect to capital R, e to the I q dot r g tilde of q. Okay. Standard Fourier transform in 3 dimensions. And of course, we already know that delta 3 of R is 1 over 2 pi cube integral d3q e to the I q dot r. I put that in here. What's del squared acting on this guy? This del is with respect to capital R minus q, iq the whole squared, so it's minus little q squared. And then I the usual game, I put that in and I argue this is a complete set of functions of capital R, so each Fourier coefficient must be 0, right. So let us write that down immediately. This will tell you that minus q squared plus k squared times g tilde of q, little q, sorry, little q, q equal to 1, because that is the coefficient of the delta function here. So it says g tilde of q equal to 1 over q squared minus k squared with a minus sign, and therefore this quantity equal to minus 1 over 2 pi the whole cubed integral d3q e to the I q dot r over q squared minus k squared. Okay. And if I can invert this Fourier transform, the job is done, g of r is done. Notice it is almost identical to what we had for the Laplacian operator where k was 0. Okay, so we just had for the del squared operator, we just had a q squared in the denominator. That q squared cancelled against the q squared from polar coordinates here, and then you got a very simple Dirichlet integral to do, but now we have a k squared in the denominator. Okay. We can still say, all right, let us do part of the integration. Let us choose spherical polar coordinates in q space. What direction should I choose the polar axis along? Well, there is a vector sticking out, the whole thing is a function of this vector, right. So I can choose without loss of generality, this is a scalar, rotationally invariant. I can choose the polar axis in little q along the direction of r. What advantage do I gain by that? I can do the phi integration immediately, it just gives me a 2 pi immediately. So this thing here is equal to minus 1 over 2 pi whole cubed integral q squared dq 0 to infinity divided by q squared minus k squared, and then there is a 2 pi factor which comes in from the phi integral, so this becomes a minus 4 pi squared, and then an integral of e to the I q r cos theta from cos theta minus 1 to plus 1, right, and that is equal to 2i sine q r over I q r. As always. So this gives me minus 1 over 2 pi squared r. So that is our first hint that we are getting somewhere, because remember for the Laplacian operator the green function was minus 1 over 4 pi capital R. So there is a 1 over r coming in here again, but that is not the end of the story, because you also have the I goes away, and then you have a q gets cancelled here, and you have 0 to infinity q, let us write this as dq q sine qr divided by q squared minus k square. We still have to do that integral. Okay. But this is not very good news, because as it stands this integral does not exist, right. Why is that? Yeah, there are poles on the real axis, there are poles on the q axis at plus k and minus k, and you can't get away from that. So this is formally infinite, and we have the same sort of problem that we had in other problems earlier, right. What you have to do is to shift the poles or indent the contour around the poles in such a way that the boundary conditions are satisfied. So you really need to find a suitable Green function by using a prescription, an I epsilon prescription for shifting the poles away from the real axis in such a way that you get the right boundary condition satisfied. Okay. So this is a sort of general lesson for all these partial differential operators. The Green functions are themselves not analytic functions, they are boundary values of analytic functions always. The Fourier transforms are boundary values of analytic functions. You need to specify some limiting procedure always. So let us see how that works, and then we will see whether we can find the Green function appropriately. So we have g of r equal to, by the way it is amply clear now that I do not need to write a vector there, because it is a function of little r, magnitude r alone. So let me just call it g of r, it is minus 1 over 2 pi squared capital R integral 0 to infinity dq q sine qr over q squared minus k squared. As it stands formally infinite. But now what is it I am looking for? I am looking for a solution which corresponds to outgoing waves. I am looking for something which goes like e to the I k r. Clearly there are poles at q equal to plus or minus k. So if I look at the contour in the q plane, the integral runs from minus infinity to infinity, but there is a pole sitting here at k and another pole sitting here at minus k. You have to shift these poles appropriately, and then there is this term here sine qr, but let us rewrite this back again in terms of exponentials, because how do I do such integrals? I do them by completing the contour and using contour integration, but I cannot complete the contour either in the lower or upper half plane as long as I have a sine qr, because this has got both e to the I qr and e to the minus I qr, and one of the two is going to blow up. So I rewrite this in terms of e to the I qr. I need not have done this, I could have retained this form minus I qr over 2I, so that becomes a 4 pi squared in this form. Okay. I hope I have kept all the factors of 2 correctly, otherwise we are in trouble. Okay. Now this term here, if I pick up the contribution from the pole at q equal to plus k, I am in good shape for this guy here. For this I must pick up the contribution from the pole at minus k, so that I get e to the I kr up on top, right. But for this, since capital R is positive, I have to close the contour in the upper half plane, and for this integral I have to close it in the lower half plane, because I want to add this well chosen 0 in the limit, this semicircle contribution, which must go to 0, and I need non-zero contributions. So it is clear that this pole here should be shifted up there, or if you like I indent the contour from below, and this pole at minus k should be shifted down here, this point, and then I take the limit. In other words, I should write this not this, but rather as equal to minus 1 over 4 pi squared Ri, limit as epsilon goes to 0 from the positive side, integral minus infinity to infinity dq. Oh, just one step, I should have written this back again as minus infinity to infinity and 8 pi squared, because I need to have a contour running all the way from minus infinity to infinity to close the contour. So I use the fact that this guy here is an even function of little q to write it as half the integral from minus infinity to infinity. Okay. So this thing now becomes as an 8 pi squared, and this becomes dq q times e to the iqr minus e to the minus iqr divided by q minus, now this pole is at, this pole here is at k plus I epsilon, and this pole here is at minus of k plus I epsilon outside the bracket. In other words, I should have written this as k plus I epsilon whole squared and take the limit as epsilon goes to 0. Okay. So I do the integral and then take the limit epsilon goes to 0. Okay. Now it should be immediately clear to you, I have two poles on the real axis on the contour of integration, and I can avoid them in 4 different ways. I can put both in the upper half plane, both in the lower half plane, or this up, this down, or this up, this down, and I am going to get 4 different green functions, but only one of them will satisfy the boundary conditions that I want, and that is the one I have chosen. I leave it as an exercise to you to play with this and do this for all possibilities. Put both up here, both down here, and see what happens. Do the other order and see what happens. You can immediately see what is going to happen intuitively. If I had put this up and this down, what would I have got? And I have got a green function which asymptotically goes like e to the minus I k r over r. That would correspond to ingoing spherical waves, right, because instead of plus k I would have chosen the minus k out here and vice versa. So this tells you how you have to have the right I epsilon prescription, how this I epsilon prescription helps you to satisfy the boundary conditions and identify the right green function. Now we are home, because this thing here is equal to minus 1 over 8 pi squared r I, and then let us write things down. I write this as q squared, so it is q minus k plus I epsilon times q plus k plus I epsilon, and look at the first term, this term here. I am compelled to close the contour in the upper half plane. That contribution goes to 0 as the radius goes to infinity, and you got 2 pi I times the residue at plus k. So you have this times at 2 pi I, this q is replaced by k plus I epsilon, but I am going to let epsilon go to 0, and then e to the I k r on that side divided by, well, this is a q minus k and a q plus k, and I have to multiply by this factor and replace q by k. So there is a 2k here, and then minus, that is this term, the contribution from this pole by closing the contour in this direction. So that is a minus 2 pi I, because I am doing this in the negative sense. So there is a minus 2 pi I. I have to keep very careful track of all the minus signs. The contribution is from the pole at q equal to minus k, so we got to put a minus k there, e to the minus iqr, but q is minus k, so this is e to the ikr divided by, it is this factor that you got to multiply by and replace q by minus k, and that gives you minus 2k here. So there is a minus 2k. There are a lot of minus signs, you have to be very careful. Now it is clear there are 4 of them, so we can make all of them plus signs. That goes away, and the contributions are identical. So it is just equivalent to saying this factor goes away and I get rid of this altogether, the k cancels altogether, the 2 pi squared cancels here, the 2 cancels with this 4, the I cancels away nicely, and you end up with a result which is minus 1 over 4 pi e to the I k mod r minus r prime, that is what r was, divided by my mod. That is it. Okay. As a check, if you put k equal to 0, you should get the Laplacian's Green function, which was minus 1 over 4 pi r. If this did not exist, the Helmholtz operator becomes the Laplacian operator and you end up with the right Green function with this boundary condition. Okay. So all that the scatter that this k squared in the Helmholtz operator does is to introduce that phase factor. Okay. And now we are home, because we can write down what our solution looks like, at least what the integral equation looks like. So you have psi of r equal to e to the I k dot r minus, now you have to remind me of all those factors that were sitting around. There is a lambda over 4 pi integral d3 r prime, the Green function, so e to the I k mod r minus r prime divided by mod r minus r prime u of r prime psi of r prime. Okay. That is the exact integral equation for scattering. It is not a solution for the wave function because it is sitting here, but it is the integral equation. This portion is the incident wave, and it is this portion that should give you the scattering amplitude. We should be able to identify that in the asymptotic limit when little r kr becomes very, very large compared to unity. We will take that up tomorrow. So from this point onwards, notice again that the entire effect of the potential is sitting here in this term, with the lambda sitting outside as a coupling constant here. This is an inhomogeneous integral equation because there is this term sitting here. Okay. And what we have to do is to deal with this equation here. Several ways of dealing with it. One of them would be to iterate, we will see what this solution looks like, but the first thing we need to know is to extract the asymptotic behavior. So I need to show that this indeed goes to e to the I k r k dot r plus f of k comma theta e to the I k r. I need to show this and extract this quantity from this term. Well, we are partly, you can see immediately partly this is going to happen, because if this potential dies down sufficiently rapidly, then when r is much bigger than all r primes, I can take out this r outside and you do get this factor. Presumably this factor comes from here, presumably, but this is a phase factor, so you can't really neglect the little r prime compared to r, you got to keep it very carefully. We make an asymptotic expansion and extract this portion here. Okay. So we will take it up from this point next time from the integral equation, and then I will say a few words about the integral equation itself, how to do this. So let me stop here today.